Thank you. Thank you, Leslie, for this very kind introduction. And thank you very much for inviting me to come here. I'm really excited to be here and to tell you a little bit about differential privacy in general and about my research then specifically in this field. So the talk, as we say, should be algorithms who protect the privacy. So algorithms, you know, are everywhere these days because every computer program and also every integrated circuit is actually implementing an algorithm. And so if you use your phone or your laptop or your home appliance or your car or your cleaning robot or certain medical devices, you will always have algorithms running there. And they're usually very useful, but they can also collect data about you, right? Now, data is also collected in other ways. For example, governments collect data about their citizens. In the US, for example, they do a census every 10 years. Or if you participate in research studies, there will also be data collected about you. This data is usually collected for a certain purpose. So for example, governments collect data so they can decide how to distribute funds or not so. Or also insurances use it to decide, you know, how much it costs to insure you, banks to make loan decisions, or doctors use AI algorithms right now in order to decide whether they should do certain medical procedures on you or not. On your phone, if you use, for example, Google keyboards, they suggest word sentence completions, and that's usually done based on data that they collected by their users. So in general, this sounds like it's great. There's certain usefulness in this data, so there's this utility, but on the other side, of course, immediately comes also the concern, what about our privacy? So you have two conflicting goals. On the one side, you can use this data to do something useful in the world. But on the other side, how can you protect the privacy? And this is really the goal of these algorithms that I will be talking about. So they want you to be able to use the data, but in such a way that the privacy of the individuals is protected. And I will try to explain to you how they are trying to achieve that. Now, what are the challenges for privacy? There's actually one challenge. Let me start with the second one here. One simple challenge is already that statistics, if they always give you exact data, might already leak a lot of information. For example, if we know the average salary of the people in this room, and then one person leaves, and then I give you the average salary again, you can easily figure out, if you know how many people were here, you can easily figure out what was the salary of the person leaving, right? Some simple math. So in general, by giving exact answers, you might already leak a lot of information that you might not want to leak. Even worse, in machine learning, very often these algorithms actually memorize data. So for example, there was some paper in 2018 by Kalini et al. Where they showed that this smart compose, which is the sentence completion in Gmail, was leaking the social security number of one of the users. Okay, because they had used trading data that had that information in it, and it happened to learn that by heart. So how can you deal with this? Well, so the first idea that people had was to say, oh, why don't we just anonymize data? Isn't that good enough? Yeah, so I might release data, but I just don't put the names. And there are all kind of famous examples that show that this was a bad idea. One of them was published by Narayan and Shmatikov in 2008. What they did was they used data that Netflix had published. So Netflix had published, so here every row was a user and every column was a movie. And so the information was whether this user liked this movie or not. And they had anonymized the data by removing the names of the users. But what these authors showed was, oh, if you combine this information together with some public information that the Internet Movie Database had, because many of the users that gave their information to Netflix also then published on the Internet Movie Database saying which movies they watched and whether they liked them or not. And they gave their names. And so if you combine these two data sources, they were able to actually figure out the names for many of the users. And they showed that basically, on average, 4 movies uniquely identify a user. Okay, so it's a bad idea to just anonymize the data, because if you combine different sources, you might be able then to de-anonymize it. Okay, so So the first idea doesn't really work by itself. Of course, you have to anonymize, but you have to do more. And so what it also shows us, this example, is that we need techniques that can handle composition of data sources, where you analyze what happens if you combine different data sources. So here were the two data sources, the Netflix and the Internet Movie Database. And then they had a second idea, the researchers, which was, can't we generalize randomized response? Now, let me explain to you what is randomized response, and then I will explain to you how they generalized it. So randomized response is a technique which was invented by Warner, a sociologist, in the 1960s, and it has been used ever since without any big privacy concerns. Okay, that's a good knowledge to have, and so for later in the talk. And so it solves the following problem. Assume you have some population and you want to find out what percentage P of the population has property A. Now, property A might be something embarrassing. You don't want to admit that you have property A, like snoring at night, for example, or worse things. Yeah, I leave it up to your imagination. So nobody wants to imagine that they have wants to admit that they have property A. Still, you want to find out what percentage P of people has this property. And now here is a solution that Warner came up with. So you have your volunteers who participate. And instead of asking them whether they have the property or not, they would just lie to you, you ask them to run this simple algorithm. So they should first throw a coin and not tell anyone about the outcome of the coin flip. And then if it was head, then they should answer truthfully. If it was was not head, then they should throw the coin again. And now they should just answer according to the coin throwing. So if it was head, say yes, and otherwise say no. Okay? But they should not tell anyone how often they threw the coin. They should not tell anyone the outcome of the first coin flip. Okay, that's the private information. And so they should just give this information back, now yes or no, depending on this algorithm. And then what you do is you determine the percentage Q of yes answers from this algorithm. And then you output 2 times Q minus a half as estimate for P, the true answer. And it turns out that this is an unbiased estimator for the true answer. So it will give you a good estimate. Now, why does this also preserve privacy? Well, because you have what's called plausible deniability. So everyone has to answer yes with probability at least a fourth. If you have the property, then you will answer yes here with probability a half here. And then here also with probability a half you said no, and then again with probability a half. So altogether with probability a fourth you will also answer yes here. So if you have the property, you will have a probability of 3/4 of answering yes. If you don't have the property, you will still have a probability of 1/4, right, of answering yes. So everyone has a probability of at least 1/4 of answering yes. So if you answered yes, and then I come to you and say, oh, you have property A, you can say, no, I actually don't have it, right? It was just the coin flips. Not me, it's the coin flips, right? You can blame the coin flips for your answer, and nobody can prove you otherwise. Okay, so it's private. And note also that you need randomization. Without randomization, this would not work, right? That you need to keep private for yourself. Okay, but randomization is very important. Okay, so now the question was, how can we make this more formal and more general? And that's exactly what differential privacy does. So it's a mathematically rigorous definition. You will see it in a second. And it measures the privacy protection given by an algorithm. And the goal is, first of all, to make it very unlikely that if you combine, that user data can be reconstructed no matter how many data sources are combined. It gives you a way to measure how much impact on your privacy the combination of data sources has. And then you can have a threshold and say, I'm only allowing so much privacy loss. And if this combination would be above it, then I'm not allowing this combination, meaning I'm not giving out my data anymore. And it also gives a parameter that tells you for each algorithm how much data leakage there is, how much privacy loss there is. And there are several current deployments, and I'll talk about this later in the talk. Okay, so now let me give you the informal definition before giving you the formal definition. The informal definition is as follows. So assume you have a database, and it has 1,000 people in it, and you run some randomized algorithm on it. Maybe computing the average salary or something, okay? And so you run some randomized algorithm on it, and it gives you some noisy answer. Okay, noisy meaning because there was some randomization involved. And now assume that you have the same database except the last person has changed. There's a new person 1000. Everything else is the same. And now you run the same algorithm on it, and you also get a noisy answer. And now what you want is that you should return the same answer for d and for d prime with almost the same probability. So mathematically speaking, the algorithm executed on the first database gives you some probability distribution on the output, potential output set. And the one on the second input gives you another probability distribution. And what you want is that these probability distributions are very close, very similar. So it's some kind of smoothness requirement on the output of the algorithms. Okay, so if the inputs are very similar, like here they only differ in the last person, then the output distributions for your answers should be very similar. Okay, and if this is the only thing you remember from this talk, you got it. Okay, I will have it again on a later slide. Now, why is this a good definition? Well, because then based on the answer of the mechanism, it is very unlikely that you can distinguish between d or d prime, that you can figure out that the input was d or that the input was d prime. You will not be able to distinguish because the output distributions are so close. It will be very unlikely that you can distinguish, I should say. Okay? That's the idea behind it. Now, more formally speaking, so we say two inputs are neighboring if they differ in at most one entry. And I will be more formal on the next slides because it depends on the application. What does it mean, one entry? Okay? And so epsilon is some number larger than 0. And now we say a randomized algorithm, or sometimes they call it mechanism, with a set P of possible outputs is epsilon differential private. So P is all possible outputs. Is epsilon differential private if for all possible subsets S of P and all possible neighboring inputs D and D prime, the probability that the mechanism started on D outputs S is at most e to the epsilon times the probability that the mechanism with input D prime outputs an element of S. That's why I gave you the informal definition beforehand, because this is somewhat of a mess. Yeah? But let me try to interpret this. So epsilon you should think of as a small number, close to 0. So e to the epsilon is just a little bit larger than 1. Okay? So what you want is the probability, and instead of saying element of S, you can just think for simplicity here that S is just one element of P and that this is equal to S. It makes it easier. So you can think the probability that the mechanism outputs an element of S is almost the same if the input was D or if the input was D prime. That's what this definition says. And the randomness here, I should emphasize, is only over the randomness of the, here for the probability, is only over the random choices of the algorithm. Okay? The input is worst case. Yeah? We are saying for all possible D and D prime. Okay? There's no input distribution. This is only on the randomness of the algorithm. And of course, because we say for all possible neighboring D and D prime, you can also by symmetry exactly get the inverse statement. Right? So you get that the probability when you started on D prime is at most e to the epsilon times higher than the probability when you started on D. So really what you get is an upper and a lower bound for the probability when you started on D. It's upper bounded by at most e to the epsilon times the probability for D prime, and it's lower bounded times e to the minus epsilon. And so if epsilon is small, close to 0, then this is roughly 1, and it gives you a good privacy guarantee. Now, one thing, however, you should keep in mind that in practice, epsilon is not as small, not close to 0. You should think of epsilon as more like 7 or 8 when used by companies. So e to the epsilon is already pretty big, but even worse, in the US Census, they used epsilon equals 19. So you might argue, well, you know, this has probability over individuals, and you know there are 300 million Americans that were counted, blah blah blah. But then you only count a subset of them anyway, and so. But still, you know, e to the 19 seems like it's a big number. Okay, but in theory, epsilon is small, close to 0. Okay, and so the crucial thing is this definition of neighboring, right? So we have this constraint on the probability distributions for neighboring data sets. Okay, so here again, this is the one thing you should remember from this talk, is differential privacy means there's a strong requirement on the output distributions for neighboring inputs. There's sort of a smoothness requirement. They need to be very close. And this is completely different from anything I've seen in algorithms before. Okay? This was not studied before, and that's why this is also such an interesting research area. We had not thought about such kind of algorithms before. Okay, now why is this useful to have this definition? So now again, informally. So assume that the user of data I is used in database D, but not in D prime. Then now you could write down, well, what is the harm for user I if the output was S? And you can multiply this with the probability that the output was S. And now you can sum over all possible S. So here you get the exact expected harm that you have if I's data was used in the database. And here you can do the same thing for D prime. D prime is where I's data was not used. And now because you know this bound here, you know that this expected harm here is multiplied with e to the epsilon is an upper bound to the harm that you get if the data was used. Okay, or said differently, any harm for user I that happens with the inclusion of data I is at most a factor e to the epsilon higher than the harm, the expected harm, without I's data. Okay, so this definition is useful because you can bound the expected harm that you have by being included. And again, epsilon close to 0 is good. Epsilon 19 might not be quite as good. Okay. And e to the epsilon is called the risk multiplier. Okay. So now what is a good definition of neighboring? Now, especially in the early days, people in differential privacy mostly looked at databases, which they thought of as tables. Okay, so they thought of tables. So you have some table, every row is a user, and every column tells you something about the user. And then the standard definition of neighboring was two databases are neighboring if they differ in at most one row. Okay, so one user is different. But then they said, isn't this maybe too generous? And they restricted it more, and they said two databases are neighboring if they differ only in the entrance for one row. So one entry in one row is different. Or even more restrictive, one entry in one row differs by at most one. Okay? And so as you notice, these definitions of neighboring become more and more specific, and thus the requirements become less and less strict, right? Because you're only required to have very similar distributions if you're neighboring. Right? If you're neighboring here, in this way, you're also neighboring here, and you're also neighboring here. While there are cases where you're neighboring here and not neighboring here. So here you have more requirements because you have more neighboring relationships than down here. Okay? And now people have studied this different kind of requirements because depending on the application that might be more suitable, and you are maybe able to get better bounds down here. Now bounds in what? Well, we'll get to that in a second. Bounds in the error that you get. Okay? So there are epsilon differential private algorithms for all of this, but the error, and I will in a second formalize the error is better if you have fewer constraints. You can handle you will get a smaller error. You might also look at graphs. Think of social networks. Each graph, each user is a node. If there's a friendship relationship, you have a link, an edge. And now you could look at vertex neighborhood of graphs, where two graphs are neighboring if they differ in at most one node. Or you can say edge neighboring, where the nodes are actually known, and you want to protect the privacy of the edges. And so you say two graphs are neighboring if they differ in one edge. Or you could just say weight neighboring. If you have weighted graphs, the graphs are actually known, but the weights are not known. And so only the weight of one edge can differ. Okay? So as you noticed while I was talking, the notion of neighboring is very closely related to what you're protecting. Right? So if you're only protecting the weights of the edges, then you're not protecting anything else. You're not protecting the nodes or the edges in the graph, meaning they might just as well be publicly known. If you're edge neighboring, then the nodes might just as well be publicly known because you're not protecting them. You're only protecting the edge relationship, who is in relation with whom. And if you're vertex neighboring, this is the strongest again, then you're protecting even the nodes in the graph. Okay, so what you protect what you want to protect immediately carries over to what's your definition of neighboring. And depending on your definition of neighboring, the more strict or the less strict it is, it will carry over to how much error you need. And since there are so many possible applications and combinations of what is the right definition of neighboring, there's lots of work to be done. Now let's go back and analyze randomized response. I claim randomized response is differentially private. The question is just for which value of epsilon. Okay. Now, but before doing that, we need to have a definition of neighboring, right? Because I told you, most important thing in the definition of differential privacy is you need to exactly specify what is neighboring. So here, for randomized response, you want to protect the bit of each individual user. Okay, so then you say two inputs are neighboring if they differ in the bit of at most one user. Okay, so think of the initial inputs here as being a string D. Then two inputs, D and D prime, are neighboring if one bit is different, is flipped. Okay, that's the neighboring definition that you would use here. Now, why is differential privacy such a great definition? Well, it fulfills two main properties. And the first property is the post-processing theorem, which says, assume you have a mechanism that is epsilon differential private, and it maps the data to some set R. And then you have some function that applies to R and computes some R prime. Then if you do the combination where you first run M and then run F on the output of M, this will be, again, epsilon differential private. Okay, so informally speaking, you had some data that was sensitive. You ran it through some mechanism that was epsilon differential private, and now the data is clean, meaning you can do any post-processing on this output of the mechanism, not on the original data. Yeah? This here does not allow F to touch the original data. F is not allowed to see the original data. It only is allowed to see the output of the mechanism. But if it only looks at the output of the mechanism, it will be fine. The whole thing, the combination of first running the mechanism and then this function is again epsilon differential private. So for randomized response, this means as follows. You can really, sorry, this was not a good idea, this animation here. So you can really break it into two pieces. The first part, which is what every participant had to do. Yeah? This is the first part. This is really the mechanism. And you get these answers, yes or no. This is the first part. This will be the mechanism. And we will show that this here is epsilon differential private. And then taking all these answers, figuring out the percentage Q of yes answers and outputting 2 times Q minus a half is just a function F. It's just post-processing, okay, of this differential private output that we got here from the mechanism. Okay, so now in order to analyze randomized response, I only need to analyze this first part. I don't need to analyze the second part. Because the second part does not look at the initial data of the real users again, has no contact to the users. Okay, so it doesn't look at the initial data, only looks at the output of this mechanism. Okay, so this is one good theorem. And now you can actually do this analysis. I will not do it. I will just say you can actually do this. You'll always look at the ratio of, if you're in there or not in there, and what's the probability that you say something, blah, blah, blah. What you will find out is that this ratio is at most always 3. Which is e to the ln 3. Okay, so for randomized response, this is your homework to do this yourself. But for randomized response, I'm a professor, right? Whenever it gets hard, it's the homework. So for randomized response, epsilon is ln 3. Okay, and I have to say there are different variants of randomized response where you would not use a fair coin, you would use a biased coin in your coin flips. And if you do this, then you can make it also epsilon differential private for any epsilon larger than 0. Just this simple variant that I showed to you was ln 3. Okay, so this is the first useful thing. The second useful property of differential privacy is composition. Okay, so assume you have a first mechanism that's epsilon 1 differentially private, and a second one that's epsilon 2 differentially private. And now you want to have a mechanism, let's first ignore G. You want to have a mechanism that just outputs both outputs, M1 and M2, the output of M1 and the output of M2. Then the theorem says that this is epsilon 1 plus epsilon 2 differentially private. And that's not too hard to show based on the definition of differential privacy. And now do your post-processing. So once you output these things, then you can now throw any function g on these two outputs. Basically, post-processing is before. And that now tells you that also some function g, arbitrary function g, based on the output of these two things is also epsilon1 plus epsilon2 differentially private. So this allows you to analyze the harm or the influence on your privacy done by having multiple mechanisms looking at the same data and outputting something about it. Okay? So if we look, for example, back to this movie data, so let's say D is the true data. So for all the users, whatever they looked at and whether they liked it or not. And then some of the data might be Netflix. Okay? So Netflix would be the first mechanism, and it discloses something. Now, as we said before, Netflix only anonymized the data, and you can show that anonymization does not fulfill epsilon differential privacy, meaning the epsilon would be infinite here. Now, the second one is the public internet movie database, and the users might not write about all the movies they have seen. So this might be, again, just some incomplete set of the true D, and that's just disclosed. That's also a mechanism. It just writes down whatever it gets. Again, not at all private. Okay, so you have a second mechanism with epsilon being infinite. Okay, so now not surprising that the combination of the two is, again, no privacy. But if this first one would have had some privacy epsilon1 and the second one would have had privacy epsilon2, then the combination of the two, having both of them out there, would be now a privacy loss of epsilon1 plus epsilon2. Okay, so this is the second very nice property of differential privacy. Now, there's one thing that people then usually ask me at this point in time, so I created a slide for it, which is there is two different notions of differentially private mechanisms. There's the one that you just saw, which is called local differentially private algorithm. It's like a randomized response. So here, the user has a true data, whether they have property A or not, and they output some noisy variant of it because they flipped this coin. So they output a noisy variant of it, and they give to the server the noisy variant, and all what the server does is post-processing. Okay, and as we know, the server can't do any harm because the data was already private. There's, however, also the notion of central differential privacy. That's more what you would see in medical databases, where the users actually give the raw data to the server, to the database. Okay, so the database actually has the true answers in it, but then it lets some differentially private mechanism run over it that then outputs a differentially private output. Okay? And so here, the difference is the server has actually the true data, versus here where the server did not have the true data, only the private data. Okay, that's the difference between the two. In this talk, I will talk about the central model, just because it's easier, apart from randomized response, just because it's easier and there was more work in the central model. But of course, now there's also lots of work done in the local model, because that's very often what happens when internet companies are collecting data about their users. It's in the local model where the user's algorithm, the user's machine or iPhone is sending this differentially private data to the server. Now, this is all great, but are there disadvantages? And yes, there are two main disadvantages. The first one is differential private algorithms are usually slower. Like before, you would have had just to say, yes, I have A or not. And now you had to flip these two coins. And I just did this with volunteers in some talk. And they had to think about when to do what. And so it's not so easy anymore. It's a bit more work. And in general, differentially private algorithms are slower than non-differentially private algorithms. And the question is just by how much. And the second, even larger problem is the loss on accuracy. Okay, so for example, which we also call error. For example, for randomized response. So what we are interested in is P would have been the true answer. Yeah? And now the way we measure the error is as follows. We say, what is the parameter alpha such that with probability at least 2/3, Q falls into this range between P plus alpha and P minus alpha. Okay, so with probability at least 2/3, Q must fall into this range. And then we say alpha is the accuracy. There's also a variant where, this is some arbitrary parameter beta. But for this talk, I'll just plug in 2/3. Okay, so the accuracy is the alpha such that with probability at least 2/3, the answer that you get will fall into this range. And of course, you want the alpha to be as small as possible because you want to be as close as possible. Okay? And so whenever you write a paper about differential privacy, you should, of course, prove that your mechanism is epsilon differentially private, or whatever notion you of privacy use. But then please also prove accuracy. Right? It's very important that you also show a bound on accuracy. I can give you an algorithm for any problem that's always epsilon differentially private. I always say 0. You know, it's definitely private. It doesn't leak any information, but it has miserable accuracy. So just writing a paper where you say, oh, you have an epsilon differentially private algorithm is not impressing me at all. You better show, that it has also small accuracy, either in theory or with experiments. Yeah? So it's a very important part, and I'm emphasizing this because I'm seeing papers where this is not done, right? And I'm kind of wondering why people would not do that. Okay, so now for randomized response, what do we get? Well, you can show actually using some Chernoff bounds that alpha will be at most some constant times square root of another constant divided by n. Okay, which makes sense. So the more volunteers you have to participate, the smaller the alpha will get. Okay, the better the accuracy will get. If I have only 3 of you, I might be very noisy. If I have 10 million, it's much better. Good, so what have we seen? So we have seen so far randomized response is ln3 differentially private, and it's O of square root of 1 over n accurate. And in general, the definition of accuracy is as follows. We say a mechanism is alpha accurate if for all inputs d, the probability, again over the randomness of the algorithm, that the true output minus the noisy output is at most alpha, that probability is at least 2/3. So there is a good chance that the error is at most alpha. And so the goal in differentially private algorithms research is always you have some computational problem. Yeah, nothing as simple as computing an average. There's something more complicated. You wanted to find the max cut in a graph, or your favorite problem. And you want an algorithm that's differentially private. It should have small additive error, so small accuracy. And the running time should be almost, running time and also the space usage should be almost as good as the best non-private algorithm. So these are the 3 things you're trying to optimize, and it's usually in that order, which means people in papers usually stop after the first 2, and sometimes already after the first. Okay. Now, there has been a lot of research. Let me stop complaining. There has been actually a lot of research in differential privacy on a bunch of problems. I will only talk about the simplest, which is the binary count in this talk here. But there are also, lots of other graph properties, clustering. Machine learning is, of course, a very hot topic. Differential private machine learning, and also mechanism design. So this is in auctions, for example. Okay. Before getting into more definitions, let me give you some deployment examples so that you're motivated to keep on listening to me, apart from having to sit here anyway. So there have been a few large-scale deployments, actually, and the first one was by Google, the wrapper system, which was in Google Chrome. These are the authors here. And they built a system in Google Chrome, and what it did was it detected the most frequently chosen home pages and also most frequently chosen running process names in Google Chrome. And that's the information it sent back in a differentially private manner, such that nobody could come to you afterwards and say, you always visit this homepage. So in a differentially private manner. Then a little bit more recently, it's in Gboard. That's the Google keyboard on Android. So if you're typing on Android, in Google, Chrome, or Gmail, you might use the Gboard. And there they did also learning for word prediction. So this is when you type in hi, and then it says the next word. Yeah? Or whatever, thank, and then comes you. Yeah, that's what they do. And here this example, hi, how are, then they suggest you. And this is also done based on differential privacy. And this is the URL of the paper where they evaluated the whole system. And they did more things, and they gave an evaluation of the whole system. Then, as I mentioned before, it's been used by the 2020 US Census. There was a lot of battle about whether they should use differential privacy or not in the census. For the 2010 census, there were some privacy leaks, some awful privacy leaks, and that's why they said, you know, the people who were running the census said we need to use some protection, so let's use differential privacy. And the statisticians always said no, and the algorithms people said yes, and argument back and forth and back and forth. And so the decision was then made, yeah, a compromise. Yeah, privacy is used, but epsilon is 19. That was the result. And now the statisticians are still very unhappy. Just recently I read an article that for some native people, right, if you have a small group, then the noise that you add makes a lot of difference. And so some native people are now complaining that, you know, based on that data, they compare the 2010 data with the 2020 data. They cannot, you know, say how much their population has really grown or where there are needs and blah, blah, blah. And this census data is usually used to determine funding for native people. So it's of course important for them to be able to say, you know, we grew so and so much. And so there are complaints about this for small populations especially. The statisticians are also complaining because some people, they complain, live in Manhattan in the Hudson River, and that should not happen either. But then the algorithm people say, it's just noise, right? It's not many. But anyway, so there are some complaints and there's some discussion, and it will be interesting to see what happens in the 2030 census. Let's see. And then there was also some deployment in Apple. And this is also one of the strange papers because it has no authors except for like Apple Privacy Research Group. Very private, I guess. Okay, and so they showed that, for example, how you can use it to determine frequently used emojis. So for example, for English speaking, if you have an English keyboard, then it seems like the smiley face here where you have tears, where you smile a lot, is very popular, but the laugh is very, only second most popular, much slower. While for the French, they smile less, but have much more laugh, for example. And so they figured that out with differential privacy. Also, they looked at, memory usage, which web pages drain their battery a lot in Safari and things like that, and in which health topics people are interested in. Because, they also sell you the Apple Watch, and they want to know, are you someone, who might be interested in health? So they also collect which health topics might be interesting. And finally, there was also work at Microsoft published by these people, and this is in Windows 10. They use this for estimating application usage statistics. And they also did so this is a picture out of their paper, a very careful evaluation. Okay, so you can see many big companies are using differential privacy already when they collect data about their users. And so now let me switch back and tell you a little bit more about the theory behind it. So I said in the static setting, the most simple problem that we are going to look at is binary count. So here what you have, you have a string, a binary string, D of length n, so think of n users, and you want to just figure out the sum, so the number of ones in the string. This is basically the same as before for randomized response, right? It was finding the population, the percentage is the same as finding how many have it and then divide by the size by n. Okay, but here I will give you now a different mechanism that's more efficient, meaning having lower accuracy. So better accuracy. So as before, D prime is neighboring if it differs from D by 1 bit. And so now it turns out there is this very nice distribution called Laplace distribution. It existed before, but it looks like it's perfect. It was specifically designed for differential privacy, which it was not, but it has only become really popular through differential privacy. So it's this function here. So this distribution, so the Laplacian distribution has a parameter here, I call it 1 over epsilon, and then you get this function. So at some value x, you get this density function here. And so what you have is you have then the variance of its sigma. And so if the sigma is very large, like here in the light blue, what you get is you get a distribution that's very spread out. Yeah. So the probability that you pick minus 10 is still, not constant, or that you pick plus 10. The smaller the sigma, the variance, the more peaky the distribution is. Yeah? I should say it's symmetric around 0, very important. Yeah? Symmetric around 0, and the more peaky it is, so the red one here, for example, is very peaky. Okay? So if you sample from it, you're very likely, probability almost a half that you pick 0. Okay. So now what is a Laplace mechanism? The Laplace mechanism is very simple. You take the true answer, the sum of the ones, and you add a random variable that you chose according to this Laplace distribution. Okay? And it turns out you can show that this is epsilon differentially private and that it's ln 3 over epsilon accurate. So why is this? What is the intuition? Well, you see, if you want good privacy, yeah, so you have small epsilon, then 1 over epsilon will be large, which means the variance of your distribution will be large. So you're more like the light blue here. Okay? So you're not too unlikely to actually add a number like 10 to your numbers. Right? You remember the input differed only by 1. Right? So you had 2 input strings that differed by 1 bit, and now you add a noise of, let's say, 10 to the 1 to the first string, the one that had this 1 bit not set, let's say. Let's say the first bit. They differ in the first bit. The first string has 0 in the first bit. The other string has 1 in the first bit. And now the probability that for the first one you picked a 10, and so you would output then whatever the true answer plus 10, and the probability that you take the second one and you picked a 9, yeah, which in this case you would then output in both cases the same thing, namely the true answer of the first one plus 10, because the second string had the first bit set. Yeah? So the probability that they're almost the same are very close, right? There are just a difference here between picking a 10 or a 9. Okay? And so you can show that by taking this parameter 1 over epsilon for the Laplace definition, you get exactly epsilon differentially privacy. It seems like it's perfectly made for that. And for the accuracy, well, you need to do a little bit of work, but not too bad. Some properties of the Laplacian distribution. Okay, but this is very nice. It's independent of n. Okay, the accuracy is independent of the size of the input. Okay, that's the nice thing here. So that's good, but what if data is dynamic? And this is now finally where my work comes in, because I like to always look at the dynamic setting where the input changes. Okay, and now people cannot agree in the field what they should call the dynamic setting. They don't call it dynamic, that's for sure. They call it either differential privacy under continual observation, or under continual release, or on streaming data, or sometimes on data streams. Okay, they're very creative, but it's all the same. It's where you get the data one after the other. Okay, so for the general model, what you have a stream of input data from the universe U of some length, let's say t. And now the privacy definition needs to be adapted. And I'll talk about this in a second. But what you need to do is every time you get some input, you need to give some output again. Okay? So before, in the static setting, you had one input and you gave one output. So you had just one chance of leaking information, right? While now you have t chances of leaking information because you need to give t outputs. After each input, after the next bit of input arrives, you need to give some output again. So let's say for binary counting, you need to keep on outputting the sum so far, the sum so far. And so you have t times a chance to leak information. So intuitively already, the accuracy should go up. You need to add more noise. Okay, so one still open problem actually is continual binary counting, and I'll tell you what's open about it. So where you have just a stream of input data 0, 1 of length t, and after the t bit is given for any t between 1 and capital T, you need to output the sum of all the bits so far. And now in differential privacy under continual observation, there are also two definitions of privacy. I'll just show you one, and I'll just mention that there's a second one. And this is the event level differential privacy, and that's very similar to what we've seen before. So we say sigma and sigma prime are neighboring if they differ in one input value, which means in one time step. In one time step, you can give something else, get something else. And then in the definition of differential privacy, now you need to say over all time steps. So before we always said over all neighboring databases, and so now we need to say over all time steps. Before we also had over all possible outputs. The outputs are now a t-dimensional vector. And then for any neighboring inputs, you have this definition again. And as it's late in the talk and I don't want to bore you too much, I skip this definition of user-level privacy, but there's a more advanced or more stringent, a harder version, which is called user-level privacy. So everything that I'm going to say now is about event-level privacy. And so now you care again about the accuracy. So what is a proper definition of accuracy for the continual setting? So now you're outputting a t-dimensional vector, right? Because you're outputting t numbers. And so the error definition that is most popular is that you take the maximum over all time steps. So if you think of this as being a vector, so this is f of sigma is the true answers, a t-dimensional vector with the true answers, and alpha is the one that the algorithm gives you. Okay, we will see this in a second. Then we will take the max, the infinity norm, which is the maximum over all the entries in these two vectors. Okay, so we say a mechanism is alpha t accurate if for all input streams of length t, the error of the true answer versus the output of the mechanism. Here for A, we plug in the output of the mechanism. That probability is at most, the difference is at most alpha with at least probability 2/3. Good, and now what's known about continual binary counting? Well, you could do it in a very naive way. The naive way would be to just at every time step, you just add Laplacian noise. This is like the static algorithm. Run the static algorithm every time. But now you're outputting t times. So, and if you do composition, right, then the differential privacy of these t outputs is the sum of the epsilon values. Okay, since you are outputting t of them, you have to make sure that each of them is epsilon over t differentially private. Okay, so you have to require at each output you have epsilon over t differentially private, which means you need to use Laplacian noise t over epsilon. Okay, and then you can just use the compositions that I showed to you before, and you get the sum over all these t outputs every time epsilon of these t epsilon numbers, every time epsilon over t, so you get that your epsilon differentially private. So that's good, but what is your accuracy? If you have Laplacian noise t over epsilon, your accuracy is t over epsilon, which is really not good. It's the number of time steps over epsilon. Okay? And the question is, can you do better? And the answer is yes, but not as good as you would like to. So what can you do? You can do an accuracy of log squared t over epsilon. That's good, much better than t. But there's also a lower bound of log t. So this was shown by Dwork, Nauer, Pitassi, and Rosblum, and this by these authors and Chan, Xi, and Song. They actually showed slightly worse bounds, but you can, basically get these bounds then. Okay, so there is actually a gap, between the lower bound. So you cannot show anything better than log t. There's this lower bound, no matter which mechanism. There cannot be a mechanism better than log t. But there is also this upper bound of log squared t. Now this lower bound of log t is actually really a disaster. Because if t goes to infinity, think of you use your phone every day, and probably hundreds of times per day. So your t, if every time they're sending some information back, whether you looked at health-related data or not, for example, then your t is very quickly very big. And this says here that then the accuracy has to go down by a factor of log t. Well, the companies who are collecting data about you don't like this, right? They don't want to have such a bad accuracy. So what they do is, supposedly, that's what they say is, every time period, let's say every month, they give every user a certain privacy budget. And then, well, whenever they use your data in some computation, they subtract something from your privacy budget. And if your privacy budget reaches 0, they don't use your data anymore. For whatever training or whatever algorithms they use, they don't use your data anymore. Until the next month, when they reset your privacy budget to be the initial value again, which means basically that they're just delaying, right, the privacy loss, right? They're just delaying it a little bit because for a while they're not using your data. But that's how they deal with it. But on the other side, if they don't want to have an accuracy error of log t, that's really the only thing they can do, because otherwise, it's too bad. Now, it turns out there's a slightly relaxed version of differential privacy called epsilon delta differential privacy, which I don't want to define. And there you can do, yeah, it's even more complicated. There you can show actually log t to the 1.5. It was shown by Changxi and Song. And so here we did some work together with Fichtenberger and Upadhyay. There, what we did is we actually figured out the constant. They had a really bad constant. We did an algorithm, a different algorithm where we showed the exact constant. And the other advantage of our approach is that our accuracy loss, so our noise is very smooth. While for the other algorithm, the noise was very unsmooth, as you can see. So for each point in t, this put a dot. Okay, and so you see that it was very unsmooth, and the reason being that the amount of noise, the number of Laplacian noises that you would add up depended on the time step, and it might even be just one Laplacian noise, or it might be log t Laplacian noises, and so you got very non-smooth noise in the setting. And in practice, it's a disaster. Assume you want to count how many COVID cases there are, right? And you don't want something where you say, I don't know whether it went up or not. Maybe it might have been the noise that made it go up, or maybe the data really goes up. So you want a noise that goes up in a smooth way and not such a jumpy way. Now let me just, because I promised, very, very high level sketch how this algorithm works. Okay, it's actually simple. Even though you might not believe it, it's our algorithm. It's very simple. Because you see, what do you want to output? You want to always output the sum of ones. Now I can write this down as a linear algebra problem, where you have a matrix A that is lower diagonal, with all ones down here and all zeros up here. And then the output that you have is simply A times sigma, where sigma is your input vector. Yeah, that's exactly the output that you want. And even better, if you are at time step t, so this is the output for all. If you do this product, you get all the answers for all time steps. If I'm at just some time step lower t, I can just take the t by t principal submatrix, so the small version of A, yeah, A sub t, where I just take the first t rows and columns, and take just the first t entries of my input, and do this product. And the t's coordinate of this product is the answer I want. So this is the correct answer. And so now how do we make this differentially private? What we do is we show that there is a composition of A into two matrices L and R, and they're both lower triangular as well. Okay, that's the crucial thing. They need to both be lower triangular to work in this continual setting. And so they also have this nice property. If you restrict them to the top t by t, you get L sub t and R sub t, and their product is still A sub t. So everything is beautifully well behaved. And so now what our mechanism does is, at time step t, it takes R t and multiplies this with the input, sigma t, and then it adds a noise vector to it. Okay? So it adds a noise vector to it here, and then it does post-processing by multiplying with LT. So our mechanism is this very simple thing here, okay, where you can prove that this is an unbiased estimator, and you can show that this is differentially private. So what we get is we get a maximum epsilon delta differentially private. We get this epsilon delta differentially private mechanism that has this accuracy. So then the whole proof is linear algebra. Okay, good. So this is what we did here. Now there has been work in the continual setting in these 5 cases. So we have data streams, which are sequences of numbers. We have databases, which are sequences of rows that have been analyzed. Data structures, where you have sequences of operations, for example, heaps. Graph algorithms, where you have, again, sequences of operations, insertions and deletions of edges. Clustering algorithms, where you have insertions and deletions of points, and you want to maintain some clustering of them. All this has been studied, but, of course, it's still in the beginning, meaning we don't necessarily have the best answers for them. So what are future directions? So one is this look at user-level differential privacy, which I just mentioned before. The other one is local differential privacy that I defined. And there has been very little work of local differential privacy under continual observation. And then also look at the running time and actually implement these algorithms and see how fast they are and how they actually perform. Yeah? So actually do algorithms engineering. And then the specific problems that I'm still interested in come up with better algorithms for clustering or graph properties. And also close the gap of this upper bound, which is log t to the 1.5 or log square t for continual binary counting, and this log t for the lower bound. Close that gap. These are the 2 specific problems I want to look at. And then I want to just thank my co-authors.